Hey y'all, so today we're going to be wrapping up kind of our second day on colors, day two, part two. The really big question that we're trying to get at is essentially why are things the colors that they are, right? So why is that when we look at something, right, we see these colors? What does that mean? Kind of what information is that telling us? How do we get those kind of effects? So we can kind of explain, like, for example, like why is the sky blue, right? Why does a rainbow have its colors? Why are the clouds white? Why is the sunset red? Why are my eyes blue? Any kind of thing like that, right? Trying to be able to explain what is going on there, what's happening, and having a good kind of thorough, rich understanding of both physically, like what does that mean about the waves that are entering my eye, but also how does my eye actually work to understand that. And last class we talked a good bit about how our eyes actually use kind of our cones to perceive these wavelengths of light and make kind of colors that we can see in our heads. Today I want to talk a little bit about just how do those different wavelengths get to our eyes, right? So why are the things the colors that they are? The one big thing that has to do with is kind of the three things that can happen to electromagnetic waves. We talked about this the other day, but I want to dive in a little bit more and talk about this. Number one is that they can be reflected, right? Now, when they're being reflected, you can either have like a smooth surface, right? There's like a mirror or any other kind of thing that's shiny. And then in that case, it's really reflecting a lot of wavelengths of light. It's a nice smooth reflection. It's clean. It comes in at that angle, and it's a nice smooth bounce. Or we could have a kind of diffuse reflection, right? So this is if we had something that was a rougher surface, in which case we get this light is kind of scattered in a bunch of different directions as it bounces off, right? Depending on where it hits and what the angle is of that point where it hits. Okay, now, so this is really big because when things have this smooth reflection, right, they appear shiny. When things have this diffuse reflection, they can appear significantly more dull. Sometimes they can appear a lot darker because not as much light can actually reflect and get back to our eyes. Okay, so that's one big thing to keep in mind. But if we have this light being reflected, right, for example, if red light is coming in or if white light, all these different wavelengths of light are coming in and only red is reflected, then we'd only be able to see red, right? Let's say that one that we had red light coming in here and one of these represented red light going over towards your eye, right? Then you'd be able to see that this thing here is red, right? So that's how reflection works, and that's an important piece. Absorption is another key part, right? Essentially, if a wave comes into a material and it stops, right? That energy is transferred to that material. In that case, it's absorbed, right? It doesn't bounce off. We can't see it, right? It kind of vanishes. It's transferred to some other form. So when electromagnetic waves or light waves are absorbed by something, we don't have any chance to actually see them. So things that are absorbing colors, it's like the colors that they're absorbing are the colors that we're not seeing, right? So if I have like my like blue water bottle here, right, this is absorbing the wavelengths that are not blue, that are like not this color. Is what this guy is absorbing. So it's kind of subtracting out those colors that I'm left just seeing what's left, right? So that's absorption. Now, one key thing with absorption that I want to come bring up is that if all light is absorbed, right? So if all wavelengths of light are absorbed, then an object will be perfectly dark. And we don't really have anything that can perfectly absorb all wavelengths of light, but we have some things that are pretty close. So for example, this material is called the Vanta black. It absorbs like 99.5% of visible light, and it is crazy. It's like here's this like mask and it's kind of like a demonstration, but you can't see any of the features. There's no like reflection on it really. It's just kind of this black like blob, right, where we can't really see what's there. We can't discern any detail, right, because of how much it absorbs that light. It's not really giving us any idea other than just like the absence of light, right? And that's kind of what that really is. And also remembering that every material, right, so this is for like red food coloring, has a kind of spectrum over which it absorbs or reflects, right? So, and we can kind of call it the absorbance versus the wavelength. So if we remember our color spectrum here, right, visible light going from about 400 nanometers to 700 nanometers. Well, here, this is like a red food coloring at 400 nanometers. It's absorbing a decent bit, still going to be reflecting some. It has its peak absorption, right? Almost 100% absorption at around like 520 nanometers, right? Which would actually, it looks like That would be like the cyan, maybe greenish. Interesting, right? Red food coloring is absorbing cyan green. Why would that be? Well, if it's absorbing these, then what wavelengths does that mean that it's reflecting? The other ones, right? Which one is absorbing like not at all? Well, that would be the red wavelengths, and that's why red food coloring appears red, is because it's absorbing all these other wavelengths and reflecting almost entirely the red. So we see the light that comes off that as predominantly red, which is kind of cool. But every material has, we can kind of have this absorption spectrum. We have that for the opsins in our eyes. We've seen that for chlorophyll before. And so essentially it's not just like one wavelength that they absorb. It's a variety, it's a range, right? But they absorb some a lot, they absorb some a little, and they absorb some like none at all, in which case they're just reflecting them. Okay, so that's something to keep in mind with absorption. And a lot of times the energy is usually just converted to heat. Sometimes it goes towards like chemical bonds. But this is kind of a big piece because if it's absorbed, it can't reach our eye. Okay. The other way that it can reach our eye, other than reflection, is if it's transmitted. So if it passes through something. Now this becomes important because like radio waves, for example, can pass through us, right? X-rays can pass through most of us, right? Gamma rays can pass through us, right? Visible light cannot pass through me, but there are things that it can pass through, right? So for example, these are like my eyeglasses here, my little prescription glasses. Okay, so visible light can actually, those wavelengths can actually pass through here. And in this case, light is passing through. Sometimes it doesn't change its path too much, but a lot of times, usually, and it depends, and we'll get more into this later on, but its path is bent to some degree. So you can actually even see kind of how this distorts, right, the light that's coming through and the vision that I end up getting. Okay, and that's because this glass, since it's a different material, the light passes through, but it does bend a little bit. Okay, this is also important in how we get how a prism can kind of separate that white light into its individual colors, or like a raindrop can do that in the case of a rainbow. Another thing that could happen with when light is transmitted, especially through like a gaseous or a liquid fluid medium, is it can be scattered, right? And I should say, sorry, so with transmission also, I should say, in the case of these, what's really interesting, these let visible light pass through and transmit through, but they don't let ultraviolet. Ultraviolet has a really hard time passing through these, right? So it's kind of interesting, right? It's kind of selective which things can pass through and which things can't, and that depends on the material that we actually end up with. But so this last one that I want to talk about is scattering, right? So this is, we have this fluid medium, light's kind of coming through, and there's all these little particles, so it can't quite come through cleanly, right? What it ends up doing is it ends up interacting with those particles and gets kind of scattered in different directions, right? So if we had blue light coming in here, maybe some of that blue light's going down there, some of it's going over there, some of it's going over there, some of it's going around doing a full 180, some of it's just going kind of straight through still, right? But it's kind of getting scattered. So it's not just going through in this kind of like straight line path, it's getting kind of scattered around. Now this is very similar to what we saw here with the diffuse reflection. The only difference is that there it's kind of limited. It can't go through the object. Here, it can't actually go through the object. So this is important for like water, for like our atmosphere, those kind of things. So when we talk about like sunsets or like why the sky is blue, right, this plays a big role in those kind of things. Now, one big note of this, right, what happens in any of these cases is totally determined by the wavelengths of light that we're dealing with, right? So visible light, white light from the sun, right, is this whole spectrum, right, of visible light is all coming down from the sun, including some ultraviolet, including some infrared, right, is coming down towards us. And what happens to those different wavelengths is totally determined by the wavelengths themselves and the chemical and structural composition of the material it's interacting with, right? Chemically, what is it absorbing, right? What is it reflecting? Is it a smooth surface physically? Is it a kind of bumpy surface, right? If it's transmitted, right, is it absorbing some things? Is allowing to pass through? Is it making it bend a lot, right? Is it scattering things a lot? This is all determined by the wavelengths of light and whatever they're interacting with, right? So we can analyze any kind of situation by looking at that, right? What are the wavelengths we're dealing with, and what's the matter that it's trying to pass through, okay? And I want to stress that it's like some things, they can reflect some light, some wavelengths of light, but absorb others. And a different material might reflect a different wavelength of light and absorb others, okay? So that's important to keep in mind. And so then the second thing about color that we've kind of talked about before is then it's how that light actually gets into our eyes, right? How our cone cells pick up those signals, those waves, and then how that's processed by our brain to actually see color, right? And that's it. That's all there is to it, right? But we can use that to explain all sorts of things. So what I'm going to have you guys do today is there's a great little kind of reading the book that talks about like why the sky is blue, why clouds are white, all sorts of different cool things like that. No need to take notes unless you guys want to, but I'd like you guys to kind of internalize some of those things. And then there's a little at-home experiment that I want you to try. And I actually did this. The experiment is kind of this link, and it looks kind of like this, right? It talks about you can mess around and kind of recreate kind of like your own blue sky and your own sunset. And what happens in that case is it has to do with this scattering effect, right? That we have right up here. It turns out that blue wavelengths of light are scattered significantly more, right, than the longer wavelengths like red. And so as the sun is like directly overhead, right, and it's kind of like a shorter path that doesn't have to pass through as much atmosphere, right, to get to our eyes. What happens is that we get blue, right, like kind of being scattered from outside. Like if you look just up kind of towards the sun, it's all kind of like white, more or less. But from the other angles, right, what we're seeing is the only way that light can get from like the other parts of the sky into our eyes is it has to go from the sun, and it has to somehow change its direction and come into our eyes, right? So it has to come down from the sun and then come into our eyes. And so the only way it can do that is because it's actually being scattered, right? It's hitting kind of these air molecules and it's bouncing off those and coming towards our eyes. Now, which wavelengths of light happen to bounce and scatter more, and therefore we see more of them in our eyes? Well, those are the blue ones, right? Now, in the case of like sunset, when the sun's lower in the sky, right, it has to pass through all of this atmosphere. And as it passes through more and more of that atmosphere, right, the blue light scatters out first, and then the green, and then the yellow, and then the orange, and we're left with this nice kind of red, right? And so that's how we get that sunset, and that reddish and that yellow-orange color on the sunset. It's because the blue's already kind of scattered out. It's all kind of faded. And the ones that didn't scatter as much, that were able to travel farther through all the atmosphere, are what make it to our eyes. And that's actually happening here. Now, I went ahead and I actually did this. I'd like for you guys to do it at home. It's super simple. But I just got like a Tupperware filled with water. I've got like a little flashlight. You can use your phone, the flashlight on your phone. And I dumped in just a little bit of milk. And I added just a little bit at first and stirred up. And this is what I got, right? And you can see in the short areas where it hasn't had to travel as far, right, you get that blue light, right, which is scattering first. And in the areas, then the blue light kind of scatters out. And then all that's left down here is kind of like that yellowish light. And then added a little bit more milk, and you can kind of get a little bit of different effect. And you can kind of play around with this and see what you end up getting. I think it's kind of cool, right? So that's one thing. I've got a few videos for you guys to watch. A Veritasium video about the world in ultraviolet, which is talking about, essentially if we could see ultraviolet, what would it look like? How is it different from regular visible light? And there's some cool stuff with that. And then there's one last video talking about from Vsauce, talking about what color are mirrors, right? These really smooth reflective surfaces. Well, what color are they? Pretty interesting stuff. And then what I'd like you guys to do for your homework, and this is the one thing that you have to submit for today, is I'm going to have you guys do a little video again. And I would just like you, and you can optionally, of course, type up like a script as always. But what I'd like you to do is I'd like you to take a video, ideally with an object, but I'd like you to pick an object, hopefully something cool. And I'd like you to explain as best as you can, in just like about a minute or so, why do you see that object as the color that you do? Why do you see that object as the color that you do? Here's kind of what I'm gonna set an example for you guys. And so what I do for mine is, this was actually today. It got a little chilly, and so I made a little campfire. And what's so cool is you kind of watch it, you see these flames just kind of like flickering. You get these yellow glowing and red and orange embers. You get these little blue flames, and there's even some like green in there. And I'm like, how is that happening? How is that actually even possible? But if you analyze it, if you look at it, here's what's going on. I'll kind of tackle it piece by piece. So what happens is, as you have this combustion reaction, there's a lot of energy that's released. And a lot of energy is converted to heat, right? And so that heat energy, it's given off mostly in the infrared at this temperature, right? Which are these darker areas? They're still really hot, but they're giving off a lot of heat in the infrared. But as they get warmer and warmer, they give off both infrared and they also start to give off actually visible light, starting in the red end of the spectrum and then going on to yellow. So these yellow parts are really, really hot, right? Now, the blue parts, right, and some of you guys may have heard that that's actually the hottest part of the flame. And while it is quite hot, the blue here, this fire is not nearly hot enough to make these embers really glow blue. This is actually coming off from it, as the logs, as the wood burns, there's some volatile, some compound, some smoke, essentially, that gets so hot and gets so excited, and the molecules that make up the smoke have particular atoms in them, right? That when they get excited, those electrons in the outer shell, they jump out, right, to a higher level, and then when they fall back down, they emit these wavelengths of electromagnetic light, right? And they happen to emit in this bluish green wavelength, and so that's why I end up seeing this like kind of blue dancing flame there. Is that's actually smoke that's superheated, right, and is excited and is emitting that wavelength of light. So that's where that's coming from. And then I have this yellow and the orange and the infrared that I can't actually see. That's coming just from these logs being so hot, right? So this is actually a light source that's coming to me. So none of it's being absorbed before it hits my eyes, right? So there's no real absorption to talk about, or reflection, until it goes into my eyes, and then it strikes my cones, right? And these yellow guys hit a little bit my red cone, a little bit of my green cone, and they say it's a yellow, right? The orange and the red, it's a lot of the red cone, a little bit less of the green cone, and these blues, right, stimulate that blue cone quite a bit and tell me that it's blue. And so that's that. It's kind of cool. It's pretty amazing, right? So excited to hear what you guys came up with, or what you guys find, maybe some colored glass, maybe like a cool object. Maybe you want to tackle like the sky or clouds, right? So I'll leave it up to you guys. Excited to see what you come up with. Hope all is well, and I'll see you guys later.